Thank you all for coming. It's a pleasure to have today here with us Dr. Petropulu, Athina Petropulu from the Electrical Engineering Department at Rutgers. And full disclosure, Athina and I actually went to school together. And Athina received her diploma in ECE from the Technical University in Athens in '86, and the MS degree and the PhD degree Northeastern University, respectively in '88 and '91. And she's been at Drexel between '92 and 2010, when, as a professor, of course, and then something happened. She wanted to become a chair. Now she's the chair of the Electrical Engineering Department at Rutgers, and I keep teasing her about it and asking her about it, but. And she's had also a lot of visiting appointments in France and Princeton. And she was also the young presidential fellow, and she co-authored the book with Max Nikias on higher order spectral analysis. She's a fellow of the IEEE and the current EIC editor-in-chief of the signal processing transactions in IEEE. And she was the IEEE Signal Processing Vice President Conference. This is a technical committee in signal processing. And she was also, I guess, right, at the ECE. She was, right? She was on the editorial board of ECE, and she was the chair of the International Conference, ICASP, that is, of 2005. And without further ado, I'm happy that she's here. Thank you. And she'll tell us about compressive sensing in MIMO radar. And I look forward to it.
Thank you, Hamid. Thank you for the introduction. It's very nice to be here to see my old friend, Hamid. As he told you, we were graduate students together at Northeastern University. Many, many years ago, over 20 years ago. But we keep in touch. I see him at conferences a lot. So as he told you, I'm a chair in the Electrical and Computer Engineering Department at Rutgers. Rutgers is in Piscataway in New Jersey. So our department has about 32 faculty, about 700 students, graduates and undergraduates. The College of Engineering has about 3,000 students, and the entire Rutgers has over 50,000 students. So it's a huge school, and engineering is a very small portion of it. So today I'm going to talk about one of the areas that I'm working on, and has to do with MIMO radar and the use of compressive sensing. I would like to acknowledge the contribution of my student, Yao Yu, who recently finished her PhD on this topic. And she finished her PhD at Drexel, and she's now a postdoc at Rutgers, looking for a more permanent position. I don't know what happened. Oh. With my computer fell asleep.
Okay.
It's good? Mm. And also I'd like to acknowledge the contribution of my collaborator, Professor Poor, at Princeton University. So we have a joint grant with Dr. Poor that is funded by the Office of Naval Research on this topic. So I will, as an outline, I will introduce MIMO radar. What is MIMO radar? Then I'm going to talk about direction of arrival and Doppler estimation using MIMO radar based on compressive sensing. Then based on a different model, I will talk about range estimation for MIMO radar. And then I will talk about measurement matrix design and discuss some future directions of work. So starting from the very basics, during a radar investigation, this kind of waveform is transmitted. So you have a narrowband signal, x of t, and a carrier frequency f of t. And if there's a target out there, the signal is reflected back and received by another receiver. And there is some delay associated with the propagation time back and forth. Beta here is the target reflectivity. It also contains the effects of the propagation from the transmitter to the target and back. So this delay is very important. It can help us locate the target. In this work, I'm particularly interested in a pulse radar. So the waveform is transmitted into pulses. So each pulse has duration. I denoted T sub p in this talk, and the period is capital T. It's called the pulse repetition interval. So I'm interested in the range of the target, the direction of arrival, and the Doppler or speed of the target. Now, traditionally, radar have been using phased arrays. Phased array consists of an array of transmitters and receivers in a fixed configuration, and they all transmit the same waveform. This waveform is multiplied by various weights at the transmit antennas so that the nodes can beamform, focus the energy into a particular direction. Now, MIMO radar, on the other hand, are using different waveforms. Again, they use a transmit and receive array, but each element transmits a different waveform. So this has some significance. Usually we discuss MIMO radar in two scenarios. One where the antennas are closely spaced together, and one where the antennas are well separated together in different locations. So let me first talk about this. In this case, the target is viewed as spatially distributed. So each antenna, each receive antenna, views a different part of the target. And the fact that we transmit different waveforms from each transmit antenna acts as exactly in multipath propagation in MIMO systems. It's unlikely that all these paths will face the same effects, as we call it, the scintillation effects of the target cross-section. So as a result, the detection performance is very good in widely spaced MIMO radar. In collocated MIMO radar, the antennas, both transmit and receive, are spaced very close together. And the target is assumed to be in the far field, and the antennas view the target as a single point. Again, they transmit different waveforms, and now the power of the different waveforms appear. It makes the array appear as if it has more elements. For example, since these transmit independent waveforms, typically orthogonal waveforms, if you go at each receive element, if you cross-correlate with each of these waveforms, let's say you cross-correlate with a waveform of node 1, then you will be able to receive information. If you have m elements here, you will receive m different views of the target just based on this single antenna. And if you have n antennas, it's as if you're receiving m times n views of the target. So you're effectively increasing the aperture of the array. So this is how the different waveforms, the waveform diversity helps the collocated MIMO radar. Please stop me if there are any questions. Now, some small background about compressive sensing. We say that a signal is k-sparse, a signal x that has L elements is k-sparse if it can be represented like this. This is a matrix, and this is a vector. This is the basis matrix. If the signal is sparse, then only a few basis vectors are needed to represent the signal. So this is a matrix full of columns. You can think of the columns as the basis vectors. And this is the vector of coefficients that basically says how significant its basis vector is in constructing the signal X. So if the signal is sparse, there are only few non-zero coefficients in this S signal. Right? So if there are only k non-zero coefficients, then we say that the signal is k sparse with respect to this basis, C. Now, there is a theory that says that if a signal is k-sparse, it can be recovered exactly from k log n measurements with high probability. And this can be done using this L1 type minimization. So what we do is we take the signal X and we left multiply it by this matrix. This is referred to as the measurement matrix. This is a fat matrix. So if this is an n by 1 signal, by multiplying it, vector, by multiplying it by m by n matrix, we get an m by 1 vector, right? M is smaller than n. So we're sort of compressing X into this vector Y. Now, if we substitute X with this in here, we get this expression, and this product is referred to as the sensing matrix. The product of the measurement and the basis matrix is referred to as the sensing matrix. And there is a principle, the uniform uncertainty principle, that says that if every set of columns in the sensing matrix with cardinality less than k, the sparsity of the signal, if any set of columns are approximately orthogonal, then the sparse signal can be recovered with high probability. So we'll see how we can apply this principle in the context of MIMO radar. So I will consider a scenario where the radar consists of nodes that are distributed on a network. Each node in the network has one antenna and can act as a transmitter or a receiver. So we have empty transmit nodes and NR receive nodes. We focus on the collocated scenario. And suppose that there are k targets out there. So some assumptions here. We'll assume that the targets are moving with constant radial speed, and the range of each target is denoted by d sub k. We assume that the targets are moving slowly, so this range will stay the same during the investigation. Now, there are different distances involved. The distance from of each target to a fixed point of the network is denoted by dk. And then we have distances from the nodes to the target. But we're going to make some simplifications here because we assume that the target is in the far field. We will, maybe I should use the. It doesn't work? Okay. Okay, so we will we will say that this distance is basically approximately equal to this distance because the target is far away, where this distance is equal to this distance minus this distance. That is a function of the distance of the receiver with respect to that center in the network and the angle of arrival. Oh, thank you. So our goal is, so during the radar investigation, the nodes will transmit something. If there's a target out there, some returns will come back. And some nodes will pick up those returns, and they will process those returns and transmit their findings to some destination, some fusion center that will make the final decision about the target. We want to minimize the amount of information that these nodes will transmit to the fusion center because these nodes usually operate with battery, and communication consumes a lot of power. So we will try to use the ideas of compressive sampling in order to minimize the amount of information that these nodes will need to transmit information about the target to the fusion center. And I'm going to describe next the basic idea of this work that appeared in JSTSP in 2010. So here is the model, the signal model. We have empty transmit antennas, and each one transmits this waveform xi. And then this is the exponential component of the waveform. And here I'm looking at the signal that is reflected by the kth target. So you have a summation over empty terms. These are the delays associated with the ith transmit antenna and the kth target. The delay also appears in the exponential. And bk is the reflectivity of the kth target. Now the signal propagates back and is received by the lth receive antenna. So because we have k targets, we have summation of k terms. Its yk is of this form. And then we have the delay associated with the return of the signal to the alpha antenna from the kth target. And if you take this expression in here, you get this double summation. And now, under the assumption that the transmit waveforms are narrowband, we can actually ignore the delay in the waveform, just maintain the delay in this exponent. And under the assumption that the targets are moving slowly, then we can get this approximation for the signal that is received at the lth antenna. So we have k targets, empty transmit antennas. This is the received signal. I can rewrite it in this form using vector notation. Put the xi's in this vector. And in here, I put all the information related to the location of the transmit antennas. So we have a summation of k terms. Bk is the reflectivity of the kth target. This is the range of the kth target. This is the angle of arrival of the kth target. This is the Doppler induced by the kth target. In here is the transmit waveforms in this vector. And this has to do with the node configuration. Now, each receive antenna will sample the signal that it receives. And it will sample and obtain capital L samples. It will sample with sampling interval Ts and will obtain L samples. And then we're going to put all these samples in this vector, which will look like this. So we have a summation of k terms, and we can lump the reflectivity of the target and the range, this exponential that contains the range. We call it gamma. And then everything else stays the same, except that now these are matrices involving Doppler, the Doppler of the target. And this expression is key in connecting this problem to compressive sensing or sparse signal recovery problem. So this is the expression for the received signal at the lth antenna. M is the mth pulse. We consider a pulse radar, right? So let's look at this signal. What if we rewrite this summation without knowing where the target is, what angle it is, what is its Doppler, and what is its Doppler shift? Then I could express this as a summation of a large number of terms. And if I discretize the Doppler and angle space, I could include similar terms here for every grid point in this space. So suppose that I have capital N grid points in that space, then I can write this summation as a summation of capital N terms, and I would have terms here corresponding to every grid point, and this coefficient here would be non-zero only for the points of the grid at which I would have targets. All the other points would have been zero. So if you think of this discretized space, this is speed or Doppler, this is angle of arrival, then if there are a few targets out there, I will have only a few non-zero gammas. Everything else, I would have zero coefficients. So here is the expression that I said. We express the summation. This is the received signal after being sampled. It's a summation of n terms. And we have all these terms multiplied by S sub n, where S sub n is equal to gamma, the reflectivity of the target, if there's a target at that particular grid point. Otherwise, it's 0. So if I can bring this in a matrix form, it's expressed like this. So the S sub n's go all in this vector. And based on this, I can construct a matrix that is given by this. Sorry. And because I expect a few targets out there, this is a sparse vector. So this looks exactly like the expression that I showed you before, which I can use to recover a sparse target using L1 norm minimization. The assumption here is that I have only a few targets out in the angled Doppler plane. And of course, there is always a criticism here. In real radar, you have a lot of clutter, and your targets are not sparse. But there are applications where, for example, if you are looking for aircraft, you focus in a particular area of space, and you don't have as much clutter. Or there are other applications where the clutter is not moving while your target is moving. And you can use that information in excluding clutter from your problem. So how would this compressive sampling be implemented in a real network? So in compressive sampling, we don't want to take a lot of data and then compress them and use only a few data. This you could do with a regular compression technique, a well-known compression technique. The idea is to obtain a small number of samples to begin with. So how is this done? This is the compressive receiver that would be implemented on the alpha antenna. So it consists of a set of filters, parallel filters. Each filter cross-correlates the signal, the received signal, with the rows of this measurement matrix. This is the equivalent operation. And then it obtains low-rate sampling, and these are the compressively obtained samples that the node will have to transmit to a fusion center. And again, the fusion center can combine all this information, the signals, the compressively obtained samples received from a number of antennas, formulate a larger problem that is still sparse, and solve it using L1 minimization.
Sorry, what is that modulating term?
So this is the row vector of this matrix, right?
Yes.
This is a matrix, and this is the received vector. So basically, each row multiplies this vector, right?
But in that phi, it's essentially the grid that you're talking about. It's all the different Dopplers.
No, the phi is not the grid. The phi, I will talk about the phi.
Okay.
The phi is typically is a Gaussian matrix. It's a random matrix. Later in this talk, I will talk about design of phi. But at this point, is a Gaussian matrix, random. The basis matrix is this. So the basis matrix is constructed based on the array configuration and based on the discretization of space. So I discretize the angle Doppler space. Right? So the idea is I expect a target at all possible points in this discretized space. But of course, I don't have a target. This is reflected in the fact that this vector is mostly 0, with non-zero elements only corresponding to the grid points where I have a target. Yes.
So I want to revisit this point. The psi matrix corresponds to the Doppler. The phi matrix you have not designed it yet in your system, and you're
No.
coming to that?
So traditionally, in compressive sensing, the measurement matrix is a Gaussian matrix,
Yeah.
right?
And you're going to design it in the remainder
Yeah,
of your talk.
right.
Okay.
I will talk about design of this.
And,
So
and how do you actually measure in your system? How does the analog measurement system work? Is that what's reflected in the block
so
diagram?
this is right. So
Okay.
this is the actual system. Now
Okay.
this is equivalent to this formulation, right? So this is in the analog domain. The signal will be passed through these filters, and these compressive samples will be generated. If we want to look at these samples from a mathematical point of view, these samples, then this is what we have. This is how they are related to the parameters of the system.
Now, if I understand correctly, the whole issue that you're utilizing is that it's easier to modulate a signal by some pseudo-random thing that's going to be in the phi matrix, and then sample it at a low rate,
Yes.
than to sample it at a high rate.
Right.
That's the key. That's
Yeah,
the key.
Exactly. Yeah.
Okay.
This is the key idea in compressive sampling. If there is interference, the recovery quality does depend on interference. This is the expression that shows the estimation error as function of the variance of the interference. So this thing depends on interference, and a good way to control interference is to use, instead of using just the random measurement matrix, to use this product where X is a matrix containing the signal waveforms in its columns. So by using this, basically cross-correlating with the signal waveforms and assuming that the noise will be uncorrelated with the signal waveforms, this will help improve the SNR. So some remarks here. The correlation of the columns of the sensing matrix decreases with the number of pulses and the number of transmit and receive antennas. So we want, just to remind you, in order for compressive recovery, sparse signal recovery to work well, the L1 normalization, we want the columns of the sensing matrix, the product of the measurement and the basis matrix, to be as uncorrelated as possible. So this correlation decreases with the number of pulses that transmit and the number of transmit and receive antennas. Now, the estimation error depends on conflicting requirements. How do I know that the targets will fall on grid points? In order to ensure that, I need to discretize the space in very small intervals. But as the grid becomes smaller, the coherence of the columns of the sensing matrix increases. So there are two conflicting requirements here that one needs to take into account in order determining the grid point that in turn affects the recovery quality. I'm going to show you some results now for a MIMO radar system that operates at 5 gigahertz. The node transmits uncorrelated QPSK waveforms of length, discretized length 512. The nodes are on a two-dimensional disk of radius 10 meters, so they are randomly located there. The reflection coefficients of the targets are all equal to 1. And we also have a jammer that creates interference. It's located at 7 degrees and transmits an unknown Gaussian waveform. So in these results, we assume that we have two targets at -1 degree and 1 degree. So we sample the angle space with increment of 0.5 degrees. And we use 30 transmit antennas. And we obtain 15 random measurements from every pulse. Actually, one pulse in this case, because the target is stationary. And I'm showing you results corresponding to one receive antenna and 10 receive antennas. And this is what we propose, the compressive sampling-based MIMO radar result. And these are based on other techniques that exist in the literature, like CAPON, APES, and GLRT. So you can see that the compressive sensing, even with one antenna, the compressive sampling-based MIMO radar, gives you very clear picture, basically no activity away from the targets. This is direction of arrival, and this is the magnitude of the reflectivity of the target. While the other three techniques give you some activity even away from the targets. If you increase the number of receive antennas, if you process jointly 10 receive antennas, the picture improves for all methods. I should mention here that these methods, the comparison methods, utilize 512 measurements from each receive antenna in order to obtain this result, while this only uses 15. So you can see, even in this case where both methods perform equally well, this can perform as well with only 15 measurements, while these require 512. Yes?
So if I understand correctly, you're saying that the prior, which induces sparsity, is very beneficial in a system in which the number of Doppler arrivals is basically 1.
Why 1?
Well, you said that there's only one arrival from 7 degrees.
No, this is the interference.
Oh, that's the interference.
Yeah, we have a jammer at 7 degrees.
Oh, okay.
Somewhere here.
Okay.
These are the targets. So what about if still here the targets are stationary, but they don't fall on my grid points? What happens in this case? So we have targets at 4 targets at these locations, and I sample in a way so that these do not fall on the grid locations. And I'm showing here results for 10 receive antennas. Again, this is the compressive sensing MIMO radar scenario, and these are comparison methods. And here I increase the number of samples that I use for the CS-based method. Here is 40, and here is 30. And you can still see that even when the targets do not fall on grid points, and I average these results over a large number of Monte Carlo simulations. So I show you mean, and the yellow area represents standard deviation around the mean. So you can see that the CS-based method works very well. This is the jammer. You don't see much activity away from the targets, and a little bit around the jammer. The CAPON method is overwhelmed by the jammer in this scenario. Same for APES. Only the GLRT works better, but still gives you a lot of variance around the targets. The music is again overwhelmed by the jammer. This is at 0 dB signal to noise ratio. And I'm going to show you some results also for moving targets. Now we have Doppler and angle of arrival to estimate. So this is the original target scene. You have 3 targets. This is angle of arrival, and this is Doppler. If I apply match filtering, now I need more than 1 pulses to process in order to estimate the targets. If I use mass filtering using 30 pulses, this is what I get. I cannot get close to the original scene. If I use the CS method with only 1 pulse, this is what I get. I cannot determine the speed, but I pretty much find the angle of arrival for the targets. If I use compressive sensing method using 5 pulses, I get exactly the original scene. So 5 pulses, and each pulse, in each pulse I obtain 30 samples. In the match filtering case, in each pulse I obtain 512 samples. So this is for 1 receive antenna, this is for 10 receive antennas. See, this is the original target scene. The match filter is not helped by the fact that I'm using 10 receive antennas and 30 pulses. But the CS method works very well. Maybe I should skip this. So the model that I considered so far, this is to remind you the model. If I have MT transmit antennas, I ignore the delays in the transmit waveforms. And as a result, I couldn't get good range estimation. I need more than 1 pulses to obtain range estimation, and still the estimation is not very well. And this has to do with the fact that the range of the target is reflected in the phase of the gamma coefficient that I had. So I cannot estimate it well. So now I'm going to show you how we can actually use a better, more detailed model that will allow us to get better range information. So we will consider the more general scenario where this is the received signal. This is the signal reflected at the target due to MT transmit antennas. These are the target reflection coefficients. And this is the range, the delay, related to the kth target. So the delay is constant, doesn't depend with time. I assume slowly moving targets, but it's still there inside the signal waveform. So this more detailed model will allow me to get better range estimation. I will also use, in order to get an even better range estimation, I will use the idea of step frequency radar. What is step frequency radar? In conventional radar, the range resolution is inverse proportional to the bandwidth of the waveform that I transmit, B. If I want to improve resolution, I have to use wideband signals. But wideband signals translate into very short duration pulses. And these pulses are very sensitive to low signal, to noise. So one approach to overcome this problem is to use step frequency radar. This means I'm sending pulses, different pulses, and each time I increase the frequency of each pulse by a certain amount, delta F. So using these pulses, I cover a larger spectrum, a larger frequency range, while each time I'm transmitting a very short duration pulse. Sorry, a longer duration pulse. So I achieve a wideband system using long duration pulses. This is the idea in step frequency radar. So we can use a similar idea, and actually we have a paper here that appeared in AES transactions this year. And the idea is along the lines that I described. We can we have M pulses. Now the received signal at the alpha antenna depends on the pulse. The Doppler of the target depends on the pulse because the frequency of its pulse changes. We have this term that contains the delays associated with this target. And I can still formulate this signal, this model, as a sparse signal recovery problem. So I discretize the angle, speed, and range space, and assuming that there are only a few targets there, I can formulate the problem into this matrix problem. This in a sparse vector corresponding to the targets present in the angle Doppler range space. And this is the basis matrix that basically of this form. Here I need to know, in this form, I need the delays of the targets. Since I don't know, okay, so I'm going to discretize this space. Since I don't know where the delays of the targets, what the delays of the targets are, I will assume all possible delays. And apply again sparse signal recovery at this point. Now there are two ways to do step frequency radar, you can use linear step frequency or random step frequency, and this has to do with how you increase the frequency in a linear fashion or in a random fashion between pulses. Maybe I will skip all this. Turns out that the linear step frequency radar gives you better error. The coherence of the measurement matrix decreases as 1 over np squared, where np is the number of pulses, while for the random step frequency radar it increases as 1 over np. So this decreases faster, which means better quality. Now, coming to the complexity, as I said, we need to discretize angle, Doppler, and range space. And this involves a lot of complexity. This type of complexity, the product of the grid points in the 3 axes to the cube, and this can be huge. So this approach could benefit from some initial information of where the target is. So one thing we could do is we could Nyquist sample 1 pulse and apply conventional methods that won't give you that great resolution, but still will give you some idea of where the targets are, and then do compressive sensing in the following pulses around the initial estimates. So that will allow us to improve the resolution significantly and reduce the complexity. So just to show you some results regarding range, because I said that step frequency radar, if we introduce step frequency radar in this case, will improve the range resolution significantly. What I show here is 6 targets. This is range, and this is the reflection, the amplitude of the target reflection coefficients. And what I show in the red line is match filtering using step frequency radar. So you can see that the resolution is not very good. The blue line shows CS-based MIMO radar that use step frequency. And you can clearly see the improved resolution. This is at 50 dB signal-to-noise ratio 25 and 0. Some ROC results. Probability of detection versus probability of false alarm. So I assume here that the probability of detection is the percentage of cases in which all targets have been detected. Probability of false alarm is the percentage of cases in which false targets are detected. So we did a large number of experiments, Monte Carlo simulations, 200 random runs. We assumed that we had 10 transmit antennas, and we obtained 10 samples at each receive antenna. We had 1 receive antenna, and we did the linear step frequency with this delta F. We had 3 targets, spaced apart by 5 meters, and so spaced apart, as you see it here. The power of the jammer is 4, and the SNR is 0 dB. So this is the probability of detection versus probability of false alarm. The red line is a match filter that uses step frequency and 250 samples in order to localize the targets. And the blue line is compressive sensing based MIMO radar that use step frequency. And this is using, I think I increase, going from here to here, I increased the number of samples that I obtained from each sample, from its received pulse, and you can clearly see the advantage of CS-based MIMO radar as opposed to match filtering based radar. Yes?
What kind of scattering environment do you consider? Are they scatterers in the environment?
No, there is no scatter. It's just the target and the transmitter.
So just line of sight?
Yes, line of sight. So maybe I can skip this to move to the next part of the work. As I already mentioned, the performance of reconstruction depends on the interference. This term here is the power of the interference. and also depends on the incoherence in the columns of the sensing matrix. So the theory says that if you use a random matrix as a measurement matrix, the results should be pretty good. You can recover the signal with high probability, but it doesn't actually tell you that there isn't a better matrix than the random measurement matrix. So we also consider the problem of measurement matrix design based on different objectives. And this is what I'm going to talk about next. And actually, this paper just appeared this month in November. December is wrong. It's November of this year in the ETRP transactional signal processing. So the idea here is we want to, we consider two criteria. One criterion is we want to minimize the coherence of the sensing matrix. So this is the average coherence of the sensing matrix. Theta is the sensing matrix. So these are the correlations between columns K and K prime, and I take the average. And this is inverse signal to interference ratio. And this is a parameter that I will control. So this is a weighted combination of inverse SNR and average coherence. And I want to find a measurement matrix that will minimize this. So if I plug in everything, I get this very complicated expression. And I can simplify it, sort of simplify it, by noticing that everywhere here I have phi Hermitian phi. So I can optimize with respect to B that is equal to this product. And also I can notice that in the denominator I have these summations that I can set to 1. So I normalize the columns of the sensing matrix to 1 by doing that. And that sort of simplifies this expression. And I can solve this problem. But again, there's a huge number of parameters involved. This is the number of parameters involved. This has to do with the number of samples that I obtain. And this is the maximum possible target delay normalized with a sampling interval. So it's a huge complexity involved in solving that optimization problem. A way to bypass this problem is to impose some structure in the measurement matrix. Instead of trying to get the optimum values of each element in that matrix, I impose this structure where this is a smaller dimensionality matrix. And this is a Gaussian matrix, a random Gaussian. So this is the unknown that I will try to estimate. So by multiplying these two matrices, I still get a sort of random structure in the measurement matrix, which I know is good. But I have a smaller number of unknowns to optimize with respect to. So another design criterion that we used is to forget about minimizing the coherence of the sensing matrix and just focus on signal to interference ratios. Try to minimize, to optimize signal to interference ratio. And again, we imposed this structure in the measurement matrix just to control the number of parameters that are in here now. And we can look at the signal to interference ratio due to the kth target. It can be expressed in this form. These are the parameters that I want to estimate. And the Q matrix is this matrix. These involve delays of the kth target and the waveforms. And this is a simple problem to optimize. I want to maximize signal to interference ratio where W has this structure. I can find a closed form solution for this problem, except that this closed form solution involves the matrix that is structured based on the delays of the kth target, and that I don't know. So what I can do is I can assume that there is the delays that I get from the various targets are uniformly distributed in this space, and then I can look at the average SNR with respect to these delays, which is expressed by this summation. And then we proposed a feasible solution not the optimal solution, a feasible solution that covers all possible delays. So based on the previous expression, I take a W matrix that is a concatenation of matrices as I found in the previous problem, except that these correspond to all possible delays of the target. And I can find the solution. The good thing about this is that my measurement matrix does not require any knowledge other than all possible delays that I expect from the targets out there. So just to compare these two designs, I have the one that I call optimal, that optimizes signal to interference ratio and minimizes coherence of the sensing matrix. And the suboptimal Phi2 that only focuses on signal to interference ratio. And obviously Phi2 is less complex than Phi1. I just want to show you some results. It turns out, if you remember, the Phi2 depends on the signal waveforms X. So depending on what kind of waveforms I use, I would get a different result. So I'm showing to you here the performance of the second, the suboptimal measurement matrix, when I use different kind of transmit waveforms, rectangular pulses, Hadamard, random QPSK. And this is a signal to interference ratio performance. And you can see that I have both theoretical and simulation results. And I compare the designed matrix to the, the blue is the design matrix, and the red is the random Gaussian matrix. So if I used random Gaussian matrix, this is what I would get. If I use the proposed matrix, I would get an advantage when using rectangular pulses. While when using random QPSK sequences, both would perform the same. So I wouldn't have an advantage by using the design matrix. This just shows how sensitive this is to miscalculating the number of delays that I expect. And again, it depends on the kind of pulses that I transmit. So while I did the Monte Carlo simulations and varied the delays, the target delays were anywhere from 0 to 100. And I used the different pulses, and turns out that for random QPSK, there is no basically penalty in estimating the maximum number of delays. I will skip this. So as future work, we're looking into node selection. The performance does depend on which nodes participate, which transmit and which receive antennas participate based on their location. So we're trying to find the optimum nodes in terms of signal to interference ratio. We're interested in target tracking. Suppose that you have a target that is moving. How do you apply this scheme with a manageable complexity? And we also consider extensions to distributed targets. So here I assume that the antennas are collocated, so the target is viewed as a single point. But we can extend these ideas when you have antennas that are far away separated, widely separated. In that case, the target is viewed as distributed. And actually, we have done some, we just presented a few days ago at Asilomar some work on this. So if you have antennas that are widely separated, the problem formulation is different. Suppose that you have a target that is moving in the XY direction, you can still discretize space and velocity of the target, and you can still express the received signal in such a form you can express it as a sparse signal, assuming that you have only a small number of targets out there. And the interesting thing is that you can still formulate it as a sparse problem, exactly along the lines of what I described before, except that there is some more information in the problem that you can use to improve significantly the performance. Like if you apply the approach, the L1 optimization approach that I described before, is basically referred to as lasso approach. We showed that by manipulating the basis matrix that enters in this recovery process, you can create groups of activity in these targets and use a group lasso approach to recover the targets, and that results in significant estimation performance. For example, based on what I said before, you have a basis matrix here, and this is a sparse vector. And these basis vectors correspond to its grid point. And you have multiple receive antennas that contribute in this matrix. So how about if you group together all the transmit antennas so that you have all the antennas corresponding to the first grid point together, all the antennas corresponding to the second grid point together. So if you do this, then this vector will be permuted accordingly, will become group sparse. So instead of having ones in totally random positions, you would have ones in continuous positions, and then zeros and ones. So you're creating a group sparse vector that like the group lasso approach results in significant resolution improvement. I just want to show you some results. So this is probability of detection versus probability of false alarm. Using match filter, you have 3 targets and 3 receive and transmit antennas. This is if you use match filter to recover, to localize, to detect the targets. This is if you used a compressive sampling approach, but without exploring group sparsity. And this is what you get if you explore group sparsity. So you get significant advantages by exploring group sparsity. And this is what you get if you increase the number of receive antennas to 4, from 3 to 4. You get a very good probability of detection. So this concludes my talk.
Okay, the floor is open. Any questions?
I'll ask another question.
All right.
So when you're talking about the resolution part of your problem, is that you're quantizing the frequency into bins, and the real location is not going to be on one of those bins. Now, there's been a lot of literature, including some recently in the compressed sensing literature, about how to identify sinusoids of analog frequencies when you have a discrete number of a finite number of measurements, and
Right.
of course the sinusoids can take arbitrary frequencies. So have you kind of looked into that type of literature?
I have not, but I know that there is work out there, yes.
Okay, so let me at least send you some link later to something that might be interesting.
Yep. Yeah,
Okay.
this is a very important problem for this formulation.
And it's a
How do you-
fundamental problem that's
yeah.
been around for 200 years. So
I have a question. In terms of the central fusion, where you basically fuse all your data to do further process your, has anybody tried to actually not do the fusion, or try to do it actually in a distributed manner?
Okay, we're looking into that. I didn't mention it, but yes, this is a very important problem. So you can obtain local estimates and locally, and then send your estimates to the fusion center.
Mm-hmm.
Right. In some cases, I showed that with one receive antenna only, you can obtain very good estimate of the target. So you could use that estimate to the fusion center. But I know that there is more involved into this, how to obtain those good local estimates. But we haven't done anything.
Any questions? Well, if there are no more questions, let's thank our speaker again.